Hi. So in the last video, we discussed conservation of momentum. When does the conservation of momentum apply? When there is no external force applied on the system. When the system is isolated, net force is zero, then you say the conservation momentum conserves throughout the event. And I gave you an example, let's say the cannonball and a cannon, right? The cannonball moves forward and the cannon actually also has a momentum backward. And I say total momentum is conserved. A lot of other cases, like you have these two balls here, right? And then they collide. This is a collision. And if I don't have my hand holding, if it's on the pool table or this is on the ground with a smooth surface, then you say it makes a nice collision. But is that really momentum is conserved all the time? When you typically just talk about only collision, right? Those collisions, when two balls get hit each other, the force, interaction force, we say, is so enormous that this governs the physics. So yes, we know that there's a gravitational force applied. There is maybe a friction force applied, right? Depends on the amount of friction, but you have a friction force applied, but compared to this interaction force of the two, those become negligible, becomes very small. But what governing the physics at that moment of a collision, these interaction forces so much more that you can forget and neglect those small external forces and treat the system as being isolated. So when the system is isolated, you can apply conservation of momentum. So when you put these two balls in a one system, both balls in a one system, and then when you discuss the event, that's just only about collision. Then before the collision, the total momentum before the collision and the total momentum after the collision is the same. The momentum is conserved. Although, yes, there is a gravitational force. Although, yes, there could be a friction force. So you could ignore the little bit of external forces, unless if it's very large compared to the friction collision force. You can ignore, and you can treat the system to be isolated and say the total momentum before the collision is equals to the after collision. So any collisions, you say you can hold the conservation of momentum. So let's share the screen, and then I'll show you. I'll write it to you. So this is chapter 6. Let's see. A little bit here. Turn on my pen. Here. Black. This is chapter 6. We're going to talk about collision. So conservation of momentum in isolated system. Where external force, we said, is 0. Then total momentum is conserved. But typically, you might have some external force. Is it really no external force? Right? How about gravitational force? How about friction force? How about other kind of force? Um, then here, in collision, sorry, just in collision, one M, in collision. The interactive force, the this interactive force of the colliding force is so large that external force, of course, such as gravitational force, becomes negligible. Negligible. Then um, you can apply conservation momentum for any collisions, typically. So momentum is conserved for collisions. Even though you might have some external forces, typically they're smaller than an interactive force. So you can say what it is that for collisions, oops, sorry, for collisions, okay, so for collisions, you say um, uh, total momentum before the collision is equals to total momentum after collision. So this is the case. When you hear collision, typically you can just treat the system that they're isolated and you say whatever the momentum, the two balls in the one system, then those interaction forces is going to be big, and Newton's third law cancels out each other anyway, so that governs the physics. And then before the collision, before colliding, after colliding, the same, the total momentum. So this balls before the collision, after collision, same total momentum of the two balls. So that's the collisions. And for collisions, though, when we're going to talk about collisions today, and the collisions, they're different kind of collision. One is called elastic collision. The other one is called inelastic collisions. So you have two kinds of collisions. Two kinds of collisions. There is one that's called elastic collision. The other one is called inelastic collision. Um, the difference of the elastic collision and inelastic collision. Let's discuss. Either way, when it says collisions, right, elastic or inelastic, because they're colliding with each other, if you put both all the particles that's colliding in one system, they're gonna hold conservation of momentum. So either elastic or inelastic, they're gonna have conservation of momentum. All right. So what makes the difference of the two? We haven't talked about energy. We haven't defined the energy yet, but here, what it is, you just have to accept it that in elastic collision. Okay, in inelastic collision. When you have an inelastic collision, you're in a collision. You momentum is conserved. All right, momentum is conserved, but often you see shape deformation, you lose that energy during a collision. So although the momentum is conserved, but you have a loss in energy during a collision. And that's called inelastic collision. But in the case of an elastic collision, like these two balls is almost elastic. It's wood, so it might be dinting a little. Like perfect example is the billiard. When you have a billiard, two billiard balls like colliding with each other, that's a good example of elastic collision. When those two balls collide with each other, they don't lose energy. There's no deformation in the shape. They don't lose much energy. So you can treat it as an elastic collision. So elastic collision or inelastic collisions, yes, momentum is conserved. Both of them, momentum. But in the case of elastic collision, what's special is an energy. There's no loss of energy is conserved. So no loss of energy during a collision. But in the case of inelastic collision, there is a loss of energy. So like shape deformation, shape deformation, or you know, um, you might lose by heat. Even the sound, you lose some energy by creating a sound when they make a collision like this. So you might lose some energy by the sound too. So that's inelastic collision. So you can kind of see that it's very rare to have a very perfectly elastic collision. You're not going to see in the real world. You always lose some kind of energy during a collision, so you don't often see that energy is complete. Collision is completely elastic. Most of the collisions is inelastic, but you could have a case that very close to elastic collision. Okay. And that's inelastic collision. So example, let me see, example of elastic collision. Here, elastic collision. example is billiard balls. So when these billiard balls comes to each other, and then this is a collision, make a collision, then so if you put all of this in one system, no loss in energy, no loss, no deformation, no generation of heat. So in this case, both um, total momentum and kinetic energy. Um, they're both conserved. Conserved before and after. Before and after a collision. Elastic. Okay. Total momentum and a kinetic energy. Both, both conserved. So that's called elastic collision. Inelastic collision, yes, energy, momentum, total momentum is conserved. But kinetic energy, which I'm going to define kinetic energy in the next chapter. Kinetic energy is not conserved. So yes, you're gonna have you may have a deformation. Yes, may have heat generation. So yes, the momentum is conserved, but and the kinetic energy is not. So that's called inelastic collision. Um, and what engineers do is to have some kind of number. So I think if you use the number like a 1, that represents the perfectly elastic collision. So there's absolutely no loss in kinetic energy, makes a perfect collision. And then you could have a case that's 0. That's called totally or perfectly inelastic collision. So here there's a collision that's called perfectly inelastic collision or totally inelastic collision. What kind of collision is this? This is the collision that let's say you have inside the inelastic collision. You could have objects like this. So this is before the collision. And then you make a collision. This is during the collision. They're colliding with each other. And then for the case of perfectly inelastic collision, they actually smush here. Objects stick together. So it becomes as one, and they share the same velocity together. It moves together. So individually, initially you might have a V1 and a V2. They have a different velocity, but after the collision, you have a bad shape deformation that they stick together and then they move together. So that's called perfectly inelastic collision. So it's the case that it's completely, perfectly, totally inelastic collision. But sometimes you have a case that you still don't move together, but then you have a loss in energy, kinetic energy, and that's called inelastic collision. Yeah. So that's the definition of two kinds of inelastic, two kinds of collisions: elastic collision and an inelastic collision. And you could have completely inelastic collision. Either way, momentum is conserved. If it's elastic collision, kinetic energy is also conserved. Inelastic collision, momentum is conserved, but kinetic energy is not conserved. Energy is used to deform the shape, generating heat, might be making a sound. You lose some kinetic energy during a collision. And in a case of perfectly inelastic collision, totally inelastic collision, then not only that you lose the energy, you don't just change the shape, but you stick together. So two objects or three objects or what, after the collision is smushed together and it moves as one. So that's called perfectly inelastic collision. Okay, so that's called perfectly inelastic collision. Let's see. I have a video that I made. This video is not perfectly perfect. It's really hard to, since I can't access to the campus right now. I don't have the perfect device, so I'm just using what I have at home quickly to show you some demonstration. And it may not show you perfectly, but you might see some. I hope I can show you some example, and I'm going to show you also the YouTube video too. So let's see, share the screen. Yeah, let me just show you my desktop. But how can I not show you the desktop? Okay, let me see. I'm gonna trying to share with you again. Quick time. Let me see. I don't think you can hear the voice, so I'm gonna share again. The computer sound. The quick time here. So I don't know, voice might not be so great, but okay. So here I have, I'm going to measure the mass. Okay, so it's 0.48 gram. 60 gram. So adding the giraffe, the total mass of the train, cargo train, and the giraffe is 60 grams. Okay, stop share. Then I'm gonna also, I also measured another object. I'll share that with you. Okay, and here. Okay, so this is 0 gram. 60 gram. Yeah, sorry about the reflection. So this is also 60 gram. So we have two objects that's same mass. One of them has a giraffe in it, so you know it doesn't act like a one rigid body. So you might see some, you know, trouble. But the thing about these two train toy is that you notice that there's a silver ends on both sides. They're magnets. So the magnets has, if you have a opposite sign, opposite polarities, they attract. Same polarity, they repulse. So I'm going to show you that. Okay. Here. All right, so in this train toy, there are magnets in it. And right now, if I put it closer, you see it's repulsive on this side. But if I put it on this side, it sticks. So this is attractive.
It's wetty.
Attractive.
It's wetty hot.
Okay. Yeah, so one side is repulsive, the other side is attractive. So when if I collide those both sides that are attractive to each other, what happens after the collision? The attractive side, both are attractive side, and if I collide both of them, it should stick to each other after the collision. And that's called what kind of a collision is that? That's a perfectly inelastic collision because each object sticks together and moves together. So that's going to be the example of perfectly inelastic collision. But if I flip it and if I have a two train that's repulsive as a repulsive magnets, then they make they're not going to actually make a contact, but there's the magnet's repulsive force that makes it collision, and that's elastic collision. So, but the thing is that you'll see. I'll show you. So I'm going to show you the example of let's see. Let's start with the totally inelastic collision. Start with the totally inelastic collision. Here it's going to be the example. Okay. Totally inelastic collision. This is going to collide. Moves together. Right? Collide and moves together. See, we don't have the perfect tools. If I were on campus, then we have a nicer two-cart system that has very low friction and has a good magnet and Velcro and all that, but we don't have that here. So, okay, so I'm going to show you one more time about total inelastic collision. Let's see. Totally inelastic collision. So when you have two objects colliding with each other after the collision, they move together. It's called totally inelastic collision. All right. So case like this, yes. And then I want to show you, I attempted to make an elastic collision um, by flipping the magnet here. Okay. Magnet is switched. It's gonna make elastic collision. Yeah, so something like that. Elastic collision. One more time. Elastic collision. Same mass, one with the initial speed, the other at rest. So something like that. I also maybe, yeah, why don't I show you that little bit of a calculation then, or ask you a question. So let's talk about totally inelastic collision, perfectly inelastic collision. Let me see. So let's see. Um, so example, perfectly inelastic collision. Collision. So we had two mass, M1 with a giraffe in it. This is a giraffe. And then M2. And M1 and M2, they're both the same, 60 gram. They're the same mass. So let's see, if M2 was at rest, this is initially at rest. So the V2, the velocity is 0. But let's say that M1 with the giraffe, has some kind of a velocity. And then they collided, make a collision. What happens to them for the perfectly inelastic collision? M1 and M2 sticks together, right? They stick together. So it becomes M1 plus M2. So what happens to the velocity of the two if there's completely one-dimensional? This new velocity will be, since the mass is twice more, right? You can apply conservation of momentum. So mass is doubled, so the velocity will be the half of the moving one. I'm sorry, half of the, not prime, half of the initial velocity of the one of the car. So you're gonna see if it's made a collision, you're gonna see that, it's gonna move together as a lot slower speed, and it's about half of the initial velocity. So that's case for the perfectly inelastic collision. What we saw is the case for the elastic collision. Case that what we saw was, let's see, in this case, again, M1 and the giraffe in it. M1 and M2, they're the same mass, 60 grams, we saw, right? We measured. And then let's say this M2 is, again, initially at rest. And M1 it's going to collide it with some kind of a velocity. And if the magnets is faced in a way to make a repulsion, they're going to do elastic collision. So after the collision, what do you expect to see if it's elastic collision? One of them is at rest. The other one has initial velocity. If it's elastic collision, what you see sometimes in the billiard balls too is that they're going to exchange the momentum, right? So what are you going to see? What's going to be the velocity after the collision for the V1 prime? What is this equals to? And what do you think? What do you think the V2 prime, the velocity of the second object, equals to? So after the collision, if it's an elastic collision, the one that was initially moving becomes 0. They interchange the momentum, and V2 instead becomes V1. So one of them, if you collide it, moves. Collide it, moves. Something like that. You sometimes see in a billiard ball like that, right? Yeah. Let's see. Something like that. So that's what I wanted to show you, but you see it's the rail that has little segments and gets trapped and stuff. So it wasn't so perfectly easy for me to show you. There is a video that I can show you from the YouTube that somebody did the high-speed exposure camera. So let me show you that. Let me see. Wait, I want to make sure that it has the sound. Okay, it has the sound. All right. So let's see. All right. Yeah, so that's what you saw is example of an elastic collision. Billiard ball, typically you can assume as it makes the elastic collision in one ball moves and another one moves, and you exchange the momentum. What if you have two of them colliding with the same velocity? So it's going to hit in about the middle. So if you're going to do this, what happens to the velocity of the two after? That's right. It should be just opposite, bounce back perfectly. What if the one object has twice of the mass than the other one. And then they make a elastic collision. What happens? So you can think about all those things, and then you can even find the exact speed by applying conservation of momentum. We know the moment we know how to find the momentum, mass times velocity. And if we know the mass, we know the initial velocity of the two. Then you can find what happens after the collision. So that's the elastic collision and inelastic collisions. Um, one more thing about collision that I want to say is, let's see, share. So we talked about in perfectly inelastic collision, totally inelastic collision. Totally inelastic collision, we're perfectly inelastic collision. You have objects like this comes together before, and then it makes a collision. And then after that, they get combined. Have we ever discussed the time sequence? Is it important? Do we need to specify it has to be 1 second before the collision or 10 seconds before the collision? No, you can pick any time frame. So in fact, you have a camera. Let's say you have a camera, and then you take a picture before the collision, and you write down inside the picture of the, you put the camera frame as your system. That's isolated. And then you take a picture and you see, okay, this object have this much momentum, this object have this much momentum. Write that down, add all of them, and you find the total or net momentum of the system. And then you don't care what's happening. Maybe they're like swimming around or going somewhere, meet the crocodile and all that stuff. And then they make a collision, and throughout, you have a no, you don't make any collision. And then you only have a one collision. And then again, after that, you can pick anytime you want. And then you take a picture again of the system that everybody is in. And then you count how many momentum. Okay, this object have this much momentum, that object has this much of momentum, including the direction. But then you add all of them, and you compare the one before, just two pictures at that particular time frame, and you say, okay, the momentum before is the same as the momentum after. The net momentum of the two is equals. So the time frame is not important. You just take a picture and you could do anything in between. That's the powerful thing about conservation of momentum, that you don't need to look at the path. You don't need to worry about what's happening in between. Just focus on the one time and then after that particular time. So in that case, it doesn't matter the time frame. Then how about this? Why don't we reverse the time? Reverse the time. If we reverse the time, what's happening is that you have an object like this, boom. And then after that, they split into smaller pieces. So this is explosion. So you see, when you have an explosion, that explosion force, I guess, same thing, interactive force in explosion is so large that you can ignore other external force like gravitational force. And then each individual after the explosion, you count all the momentum of the individuals after the explosion, it's going to be the same as the momentum before the explosion. So you can apply conservation of momentum for the explosion and treat it like the same thing as a perfectly inelastic collision. They're the same thing. In fact, you could even throw a ball in a mid-air, right? Let's say if you can throw a ball in a mid-air, so it makes a projection. This ball is going to make a projectile motion because the only force applied is gravitational force. Let's say in the middle, they make an explosion. So the smaller pieces will go all over, and then they'll fall down. And if you track all of them, the velocity of all of them and a location for each time frame, the center of mass of all the individual object follows this a parabola like path. So you could actually do that way, but because the only force applied for the free fall is, that's right, gravitational force. So even after the explosion, the only force applied is gravitational force. So the center of mass moves as if it was just the one object that has the gravitational force. But anyhow, so this is the perfectly inelastic collision, and then you say explosion also is the same. You can treat it as the same as perfectly inelastic collision. All right, so this is going to be the end of the collision video and the end of the chapter 6. 6.6, the very last section of the chapter 6, goes over the complicated, more complex case of collision. But you have to deal with the two-dimensional and things, and I don't think I want to do that. So we're going to pass that section. If you're interested, you could read about it and ask me questions, but we're not going to discuss this in the class. So make sure to read this section. It's an easy, I might expect you to do the easy calculation, like, okay, the double the mass, what happened to the speed, or be able to explain it conceptually. But that's about it. And I will assign you the part 2, chapter 6 homework too. All right, so I'm going to see you in discussion.